natural log. Yeah, I don't know why it took me so long to figure it out. You were talking about logs, so I should have figured that out, but I didn't.
Well, I should have known that.
Well, the problem is that there is a function, an inverse function. So the moment I heard IN, I was thinking inverse. It just
Yeah, me
shows you how once your brain goes towards a certain direction, it's hard to turn it around. Let's talk about the natural log.
Yeah.
Because believe it or not, that's one of the most important, probably without a doubt, the most important log.
Okay.
And what it is the log base E.
Yeah.
Now what is E? E is a number like pi. It is approximately that. But
Okay.
what it really is the limit, and you will eventually get limits of 1 plus 1 over x to the x power as x approaches infinity.
Okay.
Now, this is very unusual. Think about that for a second. As x goes to infinity, what's inside the parentheses gets closer and closer to 1.
Yeah.
And 1 to the infinite power is still 1.
Yeah.
But it never actually reaches 1. It becomes maybe 1.00000001. And if you take that to the infinite power, well, that would be infinity.
Yeah.
So this is a really paradoxical, it's like a I always call this my Superman problem, where there's two Supermen and one is an irresistible force and the other is a immovable object. And if they collide, what happens? Well, it's a paradox. You can't have an irresistible force and an immovable object. They don't exist. Well, this ends up going to 2.71 ... It's just like pi. It goes on forever. It's an irrational number.
Okay.
Now, why is this number so special? It is without a doubt the second most special number in mathematics, right behind pi.
Okay.
Is because most everything in real life follows that model. If you're talking about bacteria in a petri dish, it's going to go on that model. You're talking about radioactive decay, it's going to go on that model. If you're talking about rabbits multiplying, it's going to go on that model. That's why E is so important. Okay?
Yeah.
When you take calculus, almost everything is going to be natural log.
Oh, okay.
Okay? And there's a reason for it. I won't go into it now because you're not taking calculus yet, although I know you will be.
Yeah.
It's just that natural log kind of rules. All these other bases, even base 10. What kind of calculator do you have, Zoe?
A TI Inspire CAS.
Okay, good. All calculators prior to that only had two log keys. One was log base 10, the other was natural log. The Inspire is such a powerful machine that it can handle any base that you want. You don't even need the change of base formula, which most people need. But the Inspire will do just about anything. It'll factor stuff. It's an amazing machine. I have one myself.
Yeah.
Okay? So, when you see ln of something, it is this.
Okay.
Just know that E is approximately 2.71. It's kind of like pi is approximately 3.14. Those are always good numbers to know approximately.
Okay.
Okay? All right, let's go back and do some of those natural log problems, or whatever you want to do today.
Okay, we can maybe start with the one that we were looking at yesterday.
Okay?
So, natural log of AB squared, and AB is in parentheses, over CD.
All right. So this is an expansion problem.
Okay, yeah.
Right? In other words, when you're starting out with one log expression, it almost by definition is an expansion problem.
Yeah.
Okay? So let's start expanding this as much as we can. Well, the first thing I would do would be to turn it into this.
Okay.
Okay, I don't really need two sets of parentheses, but okay. Now
Yeah.
let's use rules 1, 2, and 3 about logarithms. These rules you absolutely have to memorize, all three of them, because you use them over and over and over.
Yeah.
So, which one are we going to apply first?
Division? I don't know.
Or multiplication. I
Division?
personally would go for the multiplication first.
Yeah, that'd probably be easier.
Well, I don't know. It's kind of like whether you want to choose addition or subtraction. Everybody does better with positive signs. Everybody makes mistakes when you introduce a lot of negative signs. Well, I kind of consider multiplication and division the equivalent of that. So,
Me too.
let's do the multiplication. Let's start separating it. So this total expression is going to equal what? I'm going to write over here on the left.
It's supposed to equal something? X?
Yeah, you're expanding it. So you're going to turn it into multiple natural log expressions. Here, I'll give you. Plus what?
Natural log of B squared.
And now let's do the division.
Natural log of C squared.
There's nothing being squared in the denominator.
Just C, yeah, of C.
Now
Plus.
what's the fourth part? No, it's not plus. It depends on whether you use parentheses or not. Okay? I'm not going to use parentheses. And we're talking division, so it's got to be subtraction.
Okay. Oh, yeah.
Okay? So that's step one. I've separated it into 4 distinct natural log functions. Now let's use rule 3 to expand it fully. So what can I do with that?
You can do A times A?
Nope. You got to know these 3 rules. Rule 3 is...
Power of a power?
Yeah. Log of A to the B power is equal to what?
Log A times B.
Put the B in front.
Oh, B log of A.
So what is natural log of A squared equal to?
2 natural log of A.
And this one?
2 natural log of B.
Minus natural log of C minus natural log of D. There's your answer.
Okay.
Now, why does order matter? If you do it the way I did it, you really can't make a mistake. Okay? The only way you might make a mistake on this is to start with and try to move that exponent over. In other words, we had this to start with, right? And the denominator is not inside the parentheses, correct?
Yeah, correct.
Well, you might be tempted to take that 2 out first.
Well, the AB is in parentheses, and then there's parentheses around the entire thing.
But what's being squared? Is it just the numerator or the denominator?
The numerator is being squared.
Okay. So if I had it, in other words, as long as this is correct,
yeah,
I might be tempted to take the 2 out and put it there right off the get-go, which is legitimate.
Oh, but
well, now what do? Let's see. It's got to be, is it 2 natural log of A plus 2 natural log of B? You don't know, really.
Yeah.
Minus, is it 2 natural log of C? You know, you just don't know. So when you have an exponent that's only affecting part of the argument, then leave it to deal with last.
Okay.
Well, I'm sure you'll have other problems that demonstrate the same thing.
Yeah.
It's another one.
Okay. Natural log of 3x plus 5 plus natural log of 3 equals natural log of x minus 5.
Okay. What's the first thing we're going to try to do here?
I don't know, since it's an equation.
Well, when you have 2 natural log expressions, you can turn it into 1.
Apply them.
So start with that. In other words, turn the left side of this equation into 1 natural log expression.
So natural log of 3x plus 5 times natural log of 3.
Which is 9. No, it's not. What you're doing is multiplying the arguments.
Just
the arguments. Yeah. So it's really this. You see what I'm doing?
Yeah.
Okay, and then this becomes 9x plus 15.
Yeah.
And if the natural log of 9x plus 15 is equal to the natural log of x minus 5, what must be true?
That x equals 3? No.
Well, give me it step by step. In other words, if you're a mathematician and you get to that, there's only one next step.
Divide?
Well, you can look at it like that, and that gets you to the right answer, but you're really not dividing. In other words, when you have the natural log of something equals the natural log of something else, then something equals something else.
Oh, yeah.
And like I said, you can kind of get away with thinking of it as dividing by natural log, but you're not really doing that. Natural log is not a multiplier.
Yeah.
Okay? But it's just kind of like if I have 2 to the x equals 2 to the 3x, the only way that can be true is if x equals 3x. It's kind of consideration that you're dealing with. Same thing when you have logs of stuff. Well, now we have an algebraic equation. You can solve this. Go ahead.
Negative 10/4.
Do it step by step so I can follow it.
So I would add 5 to both sides
Deal
And
with the variable first, because that tells you which side you're going to put your variable on. Is it the left or the right side?
On the left.
Okay, so what's your variable?
Subtract x from both sides.
So it's 8x equals what?
Wait. Minus 15. Negative 20.
Correct. And then you divide both sides by that, simplify it, and you have your
negative 10/4.
Well, that's negative 5/2.
Oh yeah, 5/2.
So you simplify it all the way down. Now, here's the thing.
Yeah.
If that violates even one domain, then this problem has no solution, because we only came up with one solution.
Yeah.
Does it violate this domain?
Negative. No, I don't think so.
I think it does.
It does?
3 times negative 5/2 is minus 15/2, which is minus 7.5. Plus 5, it's a negative number.
Yeah.
So it violates that domain. Also happens to violate this domain over here. But you wouldn't need it to violate two different domains. All you needed is to violate one of them. And if you only have one answer and it violates one domain, then it's no solution.
Okay.
This, by the way, is just a number. Never forget that. When you have the log or a trig function, it's a number. It may be a number you have to look up in your calculator, but it's still just a number. When I was in high school, we had to look it up in tables. Truly, every math book, I mean, this is the truth. Every math book had tables in the back of them, giving you all the log and natural log of any number you wanted.
Wow.
Same with sine and cosine. But now that all of that is available in calculator, they don't put that in the back of books anymore.
Yeah.
All right, what else you got?
Okay,
Maybe have one that has a solution. And, you know, it's possible that I did the arithmetic wrong on that previous one, so, you know, I wouldn't bet my life on it. But
I think there's an answer key online that I can look at.
Oh, that's wonderful. If you can look at it,
it doesn't show you how to do it. It just tells you what the right answer is.
Can you do that?
Yeah, I could check it real fast right now.
Go ahead.
Okay.
Because if I made a mistake, I want to correct it. I want to go back over the problem.
Yeah, the right answer is no solution.
All right, let's do the next one.
Okay. Wait, let me pull this back up.
I kind of hate that, and I'll tell you why. As a tutor, that is the very first log equation we have solved.
Yeah.
And to come up with no solution, that only happens 1 in 100 times. So it doesn't really teach you much.
No.
Normally you're going to have a solution. There's very few log equations that don't have a solution. So I don't like starting with the most difficult question and working our way backwards.
Well, I don't think I have another natural log one other than one that I think I know how to do now.
Let's go ahead and look at it, and I'll see whether you know how to do it.
Okay. Natural log of 3x plus 5 each equals natural log of x plus 15.
Yeah, this is pretty easy. What's the next step?
Set them equal to each other. 3x plus 5
I call this the argument. I don't know what your teacher calls it. I'm not sure what it's supposed to be called, but argument works pretty good.
Okay, so set the arguments equal to each other.
Yeah, 3x plus 5 equals x plus 15. And we don't even need to talk about that. We're not going to solve that.
Yeah.
And let me give you one.
Yeah.
And I'm just going to make this up off the top of my head.
Okay.
So I don't even know if this has a solution, but we'll see if it does.
Okay. I'll get out a paper real fast. Okay.
I would prefer if you don't get out a piece of paper.
No? Okay.
I want you to work through your thought process and tell me
Okay.
what the next line should be.
I'm a little slow when I do it out loud.
I have no problem with that. But
Okay.
I believe it's a vital part of the tutoring process, because if I can spot your weaknesses, that's something we can work on.
Okay. So I think you would start by multiplying the arguments together.
Give me the next line. When you're working equations, whether they're algebraic or logarithmic, that's what you do, is you go from one row to the next row to the next row to the next row until you have an answer.
Okay, so x squared.
Okay. So hold on a second. Conceptually, see, this is what's important. I need to know what your thought processes are. We have two log expressions that are being added.
Yeah.
So I want to reduce that to one log expression, always, if I can.
Yeah. So I think you multiply them.
Okay, so tell me in the next line.
So x plus 1 times x minus 1.
Which is x squared minus 1. So that's the next line, always. Now, what you want to do is turn it into an exponential equation.
Okay. So
what's that base?
e.
Okay, so what's the exponential equation?
E to the power of 2 equals x squared minus 1.
Perfect. So we have over here on the left, x squared equals e squared plus 1. So x equals plus or minus the square root of e squared plus 1.
And that's the simplest you can get it?
Yes, because I cannot write e as a number. E is an irrational number. It goes on forever. So if I want to be completely accurate, I'm going to leave it as e, just like you leave pi as pi.
Okay.
You don't any longer. You might have at one point in time in your math career changed pi to 3.14, but you don't do it anymore, right?
No.
They never ask you to change it because pi is a number. It's just an irrational number that can't be expressed in any way other than pi. Any other thing is an approximation. However, we're not done with this problem. Notice that I got the plus or minus.
Oh,
Approximately what's the square root of e squared plus 1?
You have to plug in 2.71 for it?
Plug in 2.71, square it, add 1 to it, and then take the square root of that.
Okay. Alright. To grab my calculator real fast.
Okay.
Okay.
Just an approximate number.
So they probably wouldn't give this to me on the non-calculator part of the test?
No, they would. You don't need a calculator for this. I'm having you do it for effect.
Okay.
What's e squared approximately?
7.3.
Okay, so if I add 1, I get 8.3.
Yeah.
So approximately what's the square root of 8.3?
How did this?
Let's see, it's a little bit less than 3, right?
2.
2 squared is 4, 3 squared is 9, So this has got to be in the high end, maybe 2.8.
Yeah.
Okay? Now, if we go up and we look at the original problem, we came up with two solutions. One of those violates the domain. Which one?
Negative 2.8.
Yeah. So we get rid of that solution because it violates the domain. And the only solution you have is x equals 2.8 and change.
Okay.
And in fact, my solution, if I wanted to express it as a mathematician would, it would be e squared plus 1, the square root of that. That is the only solution.
Okay.
And that is a more typical log equation that turns into a quadratic.
Yeah.
And then you get two solutions from almost all quadratics, give you two solutions. And almost always, one of those solutions is going to violate the domain. So you got to get. So this problem teaches you a lot more than the other problems you've had.
Yeah.
Just tell you no solution. That doesn't teach you much.
No.
All right. What else?
All right.
And anything. Doesn't have to be natural logs. Whatever else you got.
Okay, so this is another expand or condense.
Okay.
This one's log base 5 of 7 plus 1/2 log base 5 of x minus 3 log base 5 of 2.
Okay. Now, this is it an expand or compress?
Compress.
Yeah, I'm going to end up with one log function.
Always?
That's it. I can combine everything because everything is being subtracted or added or has a coefficient in front of it.
Yeah.
Okay. So when you're faced with compressing it, I found the best thing to do is to get rid of that leading coefficient. So let's do that first. What's the second term going to be?
To the log base 5 of x to the power of 1/2.
Yeah. And what's the third term going to be?
Log base 5 of 2 cubed.
Okay. Now, we don't have any more coefficients.
Yeah.
So we can turn this all into one expression. Combine the plus and the minus to make multiplication and division.
So 7 times x to the 1/2.
Notice that 1/2 only affects the x. It does not affect the 7.
Divided by 2 cubed.
Which is 8.
8, yeah.
There's your answer.
And that's the most simple
answer. I cannot reduce it any. I can represent it a little bit differently. If you were looking at a multiple choice test, you might see this. And it would be important that you recognize that this is the same as this.
Yeah. It's not going to be a multiple choice test. But
well,
I recognize that.
Yeah, when I say that, sometimes if they start with radicals, they want their answer in radicals.
Okay.
Now, this one didn't really start with radicals. It only ended up that we could turn that into a radical if we wanted to. So this would probably be the best answer right here.
Okay.
Another thing is as you go further in mathematics, you use radicals less and less frequently. what you do is use fractional exponents.
Oh.
And the reason is in calculus, the very first step for taking an integral or a derivative is to look at the exponent and use it. So radical x doesn't mean a whole lot in calculus, but x to the 1/2, I can work with that.
Yeah.
So that's just another note on radical signs. And pi and e. What else do you have?
Okay. This is another challenge problem from yesterday, or a few days ago. 1/3 to the power of x plus 4 divided by 27 to the power of 3x minus 6.
What is similar about these two numbers?
I know that you can change 1/3 into 3 to the power of -1 and 27 into 3 to the power of 3.
What's common? In other words, these two numbers have a common exponential base of 3.
Yeah.
And whenever you're looking at a problem like this, see if you can find a common exponential base. Tell me what the common exponential base is between those two numbers.
2.
Yeah. In other words, I can write this as 2 squared and I can write this as 2 cubed.
Yeah.
That's what I mean by common exponential base. It's not factor, it's base. Exponential base. Okay? So, therefore, I'm going to do the following. I'm going to turn this into 3 to the minus 1 instead of 1/3.
Yeah.
To the x plus 4.
Yeah.
All divided by 3 cubed, which is 27, all to the 3x minus 6. Now, simplify those. What is 3 to the minus 1 to the x plus 4 equal to?
3 to the negative x minus 4.
And what is 3 to the third to the 3x minus 6 equal to?
3 to the 9x minus 18.
Whoops. Now, I've got same base, different exponents. What do I do with the exponents?
Divide?
Or subtract? Here, let me teach you one rule that'll come in really handy. You never do the same thing to the exponents that you're doing to the base.
So is it subtract?
It has to be. It's not division, because we're dividing the base. Okay. So my answer is going to be that base 2 minus x minus 4 subtract 9x minus 18.
So the bases don't cancel, they're still the base of 3?
Yes, it stays the base. It's kind of like when you're adding fractions. If you're adding 3/4 to 6/4, you've got 9/4. The denominator stays the same. Same thing when you're working with exponential stuff. As long as the base is the same, then you can work with just the exponents. Okay, so what does this come out to be?
Negative x minus 4 minus 9.
Okay, well, our goal is to remove the parentheses and end up with an x and a number.
Oh yeah, okay. So, negative 10x plus 4 plus 18 plus 14.
Good. There's your answer.
Oh, okay. So you don't have to solve x for anything?
No, and mainly because of this. They didn't give you an equation. They gave you an expression.
Oh, yeah.
Okay? Usually when they give you expressions only, You don't have to solve for, you can't solve for x. It's an expression.
If it is an equation, then you always solve for x, right?
Yeah. If it's an equation, you usually can solve for x.
Okay.
But this is not. It wasn't like equal to 1 or anything. Then I'd be able to solve for x. But
what if it was equal to something?
I'm sorry, what?
If it was equal to something, then how would you do it differently?
Well, you end up getting your exponential. Do you remember what it was? It was 3 to the minus
10x plus 14.
Okay. Let's say that's equal to 10.
10? Okay.
Yeah. How do you solve that? You're trying to solve an exponential equation, not an algebraic equation. When your variable is in the exponents, you can't solve it algebraically. What do you have to use?
Logs?
Yes.
So
whenever you're trying to solve an exponential equation, most of the time you have to use logs. Sometimes you could not use logs. If I made that a 9 instead of a 10, I'd be able to solve this without logs because I have a common base of 3.
Yeah.
And I could make the 9 read 3 squared. But it's 10. It's not a common base. So the only way to solve this is by using logs. And I mean that. That's why logs were invented.
Yeah.
Okay. So how do I solve this using logs?
Log base 3 of 10 equals negative 10x plus 14.
Well,
is that right?
Not quite. First of all, what I'm going to do is I'm going to take the log of both sides of this equation. Okay. I could use log base 3, but it's really not the best one to use. The best one to use is always natural log.
Oh.
Just telling you. You're going to have some problems where sometimes it's correct to use log base 3, but natural log is always correct, and believe it or not, it's always just as short as any other method.
Okay.
Okay. So, and I'll go through this problem more after we go through it once.
Yeah.
So, just like any algebraic equation, you can do anything you want to one side as long as you do it to the other.
Okay.
What I chose to do was take the natural log of both sides.
Yeah.
Now, use your log rules to get this variable out of the exponent.
Wait.
This variable's in the exponent. As long as it's in the exponent, I can't work with it. But if I can get it down on the algebra line, I can work with it.
You can put it before the natural log?
Exactly. In other words, that's rule 3. You with me?
Yes.
Now, that's a number, that's a number.
Yeah.
Let's divide by that number. With me?
Yep.
Now the rest of it's pretty simple. In other words, you're going to subtract 14 from both sides.
Wait, so it...
Okay, hold on. Let me rewrite this so I have room. Remember, the right side is just a number. Nothing special. It's a number you can get out of your calculator.
But you can't, like, say it's natural log 7 because you subtract?
No, definitely not. Notice, I'm glad you brought that up. Because if I had, and you don't subtract, you divide. But if I had the natural log of 10 minus the natural log of 3, which I can understand why people would make that mistake, that would actually be the natural log of 10/3.
Oh.
Not the same as what we're looking at. We're looking at the natural log of 10, which is a number, divided by the natural log of 3, which is another number.
Yeah.
So be careful about these log rules, but definitely learn them and learn them by heart. You have to use them over and over.
Okay.
So we're down to this. Now, if I want an exact answer, I'm going to start by trying to isolate x, right?
Yeah.
So I'm going up here. I'm going to subtract 14 from both sides. That's a number. I'm going to leave it as is because that's the most accurate there is.
Yeah.
Now what's the last step?
Divide by -10.
Exactly. There's your answer right there.
Oh, okay.
I know it looks complicated, but if I try to make that any simpler, I could turn that into a number, but it would be an approximate number. It would not be an exact number.
Yeah.
Notice that I can get the natural log of 10, I can get the natural log of 3, and then I have a number minus a number all divided by a number. So I could definitely turn that into a decimal number, but it's not an exact number. It can't be exact. I don't care if I go out to 25,000 decimal places, it's still going to be rounded off. So if you want exact, and math, they want exact. So once you reach a certain level at math, and you're probably there now, you're not rounding this stuff off. You may round it off in your head just to get an idea of what that number is, but you're not going to round it off in an answer. It's always going to come in exact form. Okay?
Yeah.
All right. Let's see. What time? Yeah, we got 12, 13 minutes here. What else you got?
Okay. I have one more problem.
Yeah.
2 log base of 3 times 3x plus 4.
Hold on a second. Remember,
or of 3x.
Yeah.
Of 3x.
Times. It's okay.
Plus log base 3 of 4x plus 1 equals 5 log base 3 of 3x plus 4.
I don't care how long I've been a tutor. I cannot force myself to start far enough to the left. Okay. We'll get there on my second row. Okay. First of all, let me point out one thing. If these are not all the same base, you cannot use any of those log rules.
Okay, but they are.
They have to be the same base. And that's all they'll give you. They won't give you problems like this with different bases.
Okay.
So what's our first step going to be?
Do you have to subtract the 2 log base 3?
Always be thinking compress or expand.
Well, I think
log expressions being added. That means I can turn that into one log expression.
But I have to get rid of the 2. So we do.
How do I get rid of the 2?
Square the log base 3 of 4.
You see what I did? I crossed out the 2 and made it the exponent. Now combine those 2 log expressions into one.
So log base 3 of 3x plus 4 times 4x plus 1.
Hold on. No, it's 3x plus 4 squared.
Oh, squared, yes.
Times 4x plus 1.
Equals.
Now let's go ahead and compress this one.
Log base 3 of 3x plus 4 to the power of 5.
Okay. Now we have our ideal situation where we have the log base 3 of this thing equals the log base 3 of that thing. What can I do?
Are you supposed to simplify the
Get rid of the logs. In other words, turn it into an algebraic expression.
So 3x plus 4 squared times 4x plus 1 equals 3x plus 4 to the power of 5.
Yes. Now, can I simplify that?
Yeah, I think so. Or
what can I do?
Well, to the power of 5 is a lot to write out.
Don't do it that way. Never do it that way. Whenever you see something raised to the power of 5, the solution never lies with multiplying it by itself 5 times.
Okay.
What do we have over here? We have a 3x plus 4 squared.
Oh, yeah.
3x plus 4 to the 5th. So divide both sides by 3x plus 4 squared.
So then it would be 3x plus 4 to the power of 3?
Yeah. So first of all, we still have this 4x plus
4.
Plus, is it? I think it's 1. Yeah.
Yeah.
Equals 3x plus 4 to the power of 3. Now, that's not simplified.
No.
So in order to solve that, we do have to expand the binomial on the right side. In other words, we have to cube that. Because then we're going to end up with a cubic function.
Yeah.
The problem is, why would they give you this problem? You don't know how to solve cubic functions yet. They haven't taught you that.
No, I don't think so. Unless, I mean, we know how to like...
They haven't, because that's actually a really, really significant step in mathematics. When you go from solving quadratics to solving cubics, it's like going from algebra to calculus. There's no such thing as a cubic formula, like there is a quadratic formula.
Yeah.
So cubics are notoriously difficult to solve, except maybe 1% of them where you can solve by grouping. Have you ever solved a cubic by grouping?
Yeah.
Okay. Like I said, that applies to maybe 1% of cubics. Most of the time, solving a cubic equation is like a 20-minute problem.
Oh, wow. Okay.
So, as opposed to a quadratic, where no matter how complicated a quadratic I gave you, you could solve it in 5 minutes with your calculator, right?
Yeah.
And using the quadratic formula.
Yeah.
Not true of a cubic. A cubic can be a 20-minute problem. I can give you a cubic that might be a 60-minute problem. It would take you 60 minutes to solve it. There's that much work and that many steps. So yeah. I'm at a point now where why are they giving you this, which is going to result in a cubic?
I'm not sure.
I know it'll be a cubic because when you cube a linear function, 3x plus 4, you end up with a cubic function.
Yeah.
Always. And then you're going to have some number of x cubed. Looks like you'd have 27x cubed. Then you're going to have a bunch of other terms. Then you're going to combine everything, and you're going to have a cubic function. 27x cubed plus some amount of x squared plus some amount of x plus some number equals 0.
Yeah.
You're going to be faced with solving that. And the only way at this point that you have of solving that kind of an equation is if it can be grouped. And the only time grouping ever works is if the ratio of those first two coefficients is the same as the ratio of the last two coefficients, which is almost never.
Yeah.
That's just not even hardly a legitimate way to solve cubics, because it never happens. When you get to precalculus, they'll teach you how to solve cubics, and you're going to be amazed at how hard it is. Which brings me back to, why are they giving you this problem?
It was a challenge problem.
Well, okay, I get that. But even still, when they haven't taught you how to solve a cubic and they're giving you a cubic to solve, perhaps maybe you can solve a cubic on that Inspire. It'll do most anything. It'll solve any quadratic for you. It'll factor any quadratic. I wouldn't doubt that it can solve a cubic. In fact, I can go to Wolfram Alpha. You do it here. 4x plus 1 equals 3x plus 4 cubed. If you're not familiar with Wolfram Alpha, let me introduce you to it. It's a website that is super, super valuable.
Yeah.
Remember what that was? 4x plus 1 equals,
I think, 3x plus 4
cubed.
Yeah.
The beauty of Wolfram Alpha is when you put it in with great difficulty, making sure you keep track of all your parentheses, it tells you what you put in, unlike your calculator. So is this what our input should have been? And the answer is yes. Now they will solve that for you and give you your zeros. There is one real solution, which is x equals minus 1.9669 rounded off. And there are two imaginary solutions, which you frequently get when you have a cubic. You know you're going to have three solutions, and imaginary solutions always come in pairs. So usually you have one real and two imaginary, or else you have three real.
Yeah.
But that's the only, when you have a cubic, you almost always have at least one real solution, because imaginary solutions come in pairs. So you can't take a cubic and have, two pairs of imaginary solutions. The most number of solutions any polynomial can have is the degree of its largest
exponent?
Yeah. And in this case, if you look at this up here, we can tell this is a cubic because that's x cubed.
Yeah.
And as all they're doing is solving that. Like I said, we would not be able to solve that. I could subtract 4x plus 1 from both sides, but I'm not going to get anything that is a cubic that I could solve without a calculator. And in fact, this looks like one of those 1-hour problems. And the reason I say that is because the solution lies on factoring the coefficient of the x cubed and factoring the coefficient of the number.
Yeah.
Now, if 64 was the number, that'd be horrendous because you got like 25 different factors of 64. And you have a lot of factors of 27. So this is going to be one of those that would be extremely hard to solve. But Wolfram Alpha does it for us. So this is a clever site. Do you use anything online? Do you use this other one that's Desmos?
Yeah, I use that sometimes.
I don't know if Desmos is as good as Wolfram Alpha or not. It might be. I think Desmos allows you to input it without having to do all those parentheses. In other words, when you have exponential stuff, it shows you it's an exponent.
Well, couldn't you just graph it on your Inspire and see where it crosses?
Well, this does that for you also. Ooh. The reason it didn't do it for us this time was because we had two complex solutions. It kind of graphed it. You see this right here? That's the graph of it.
Yeah.
Gives you the real solution. It occurred at minus 1.9669. And it gives you the two imaginary solutions. When you're graphing imaginary solutions, your vertical axis is the imaginary, your horizontal axis is the real.
Yeah.
So I don't know what Desmos would give you if you put this in. Might be worth looking at it, but I'll leave that to you. Wolfram Alpha may have some advantages over Desmos. I can't be certain because I'm not that familiar with Desmos. I end up using Wolfram Alpha a lot, though.
Okay.
Especially when you're trying to find the zeros of cubics or quartics or anything like that.
Okay.
Even quadratics, it's nice because it'll graph it for you. It'll tell you the real zeros. It'll tell you both zeros. And most importantly, it gives you that input where you can see that you're getting what you wanted.
Yeah.
All right.
Okay.
Zoe, I will let you go and have a good rest of your evening.
Thank you so much.
You're welcome. Bye-bye.
Bye.